Hi, and welcome to Lunch and Learn with Vince. My next guest is Larry Bachus. Larry is a good friend of mine, an extremely accomplished pump engineer, inventor, writer, speaker, teacher, trainer. Larry's done it all. I'm telling you guys, this is something you want to tune into and save this. So if you like what you're seeing, like and save. Once again, welcome to my Lunch and Learn with Vince. Larry, welcome to the
Hello.
show.
Hello, Vince. How are you doing today?
Great, good to see you. Can you tell us a little bit about what we're going to talk about today? I think it's dual.
We're going to talk about options that you must ask and answer as you go to buy a product, and then we'll talk about pumps, some of the options that you must consider as you go to buy a pump.
Okay, perfect.
All right.
Well, let's just jump right in. The dual volute, I believe, is the
that is today's discussion.
Yeah.
Should we go to the PowerPoint now?
Absolutely.
All right.
While we're getting started here, the show that we did with the shaft, what was it? Oh my gosh, the one we did with the
wasn't that the couplings?
Coupling, thank you.
Couplings, yes.
All right, see, I have gotten some incredible feedback from very, very good people and industries that make huge motors that are all over the world. Okay, these motor companies have complimented you on that coupling discussion. So not only people in the coupling industry have seen it, people in the motor industry, and they watched and hung on every word, Larry. So these are working, and I just want to compliment you. The information is helpful. So please like and subscribe, and we're just going to take it from there. So go ahead, Larry.
Okay, yeah. Well, let me say, I represent pump users. I represent the interest of pump users, people who must use and maintain pumps. I don't necessarily represent the interest of the manufacturers of any of the pump products. I almost have no opinion about them, but I know that if I were in charge of this equipment to use it and to maintain it and to improve the reliability, I would do certain things that might be different from what the manufacturer or the distributor might say.
Well,
so that I represent the pump users, not a pump company or a seal or coupling company.
I'm so glad you brought that up. I did a podcast last week with a lubricant specialist who has literally been all over the world, and in a similar fashion, he said, just because the original equipment manufacturer has said that this is the weight in the lubricant and the viscosity and all that, when issues arrive, a professional can go in there and tweak that recipe a little bit and get a much better result. And we're here to talk about that in the same way. So go ahead, please.
Okay. Well, single versus dual volute pumps. If you want to purchase something, you're going to have it'll have some options. If you're going to buy a TV or a mattress, then it's going to come with some options, and you may have some questions. And if the sales rep can help you to answer the questions, then you'll buy the product that you want and that you need, and it'll have the features that you want. For example, with a new car, today, a sales person would say, do you want the gasoline engine, or do you want a hybrid, or do you want a totally electric vehicle? Most of the car companies can offer that in one or two of their models, okay? And do you want a two-door or a four-door? Do you want a sedan or an SUV? You want automatic or manual transmission? And this is just to buy a car, and some other questions, okay? Now, likewise, in the chemical process industry, pumps are offered with some options. And the purchaser, a purchasing agent, a manager, materials person, or an engineer must select the options that are compatible with the liquid and the process. Now, for example, a pump might be available with optional impellers. And the sales rep could ask, do you want this pump with the enclosed impeller or with the open impeller? And the customer might say, I don't know, what's the difference? And the sales rep could say, well, the enclosed impeller with wear bands is going to be best if the liquid is clean with no solids, crystals or sediment or dirt in the flow. And the wear bands on the enclosed impeller will improve the pump's efficiency. So that may lead you to purchase that. However, if the liquid contains solids, rocks and sand and mud, then the open impeller would probably be best because it won't clog with the solids. And now the purchaser can make a better decision with the information provided. Another typical option available in the purchase of a pump would be, do you want this pump available with the single volute or the dual volute? And many people don't know the difference. And it's a common question. Why would I want one? Why would I want the other? And I do find that frequently the incorrect pump is bought. So we're going to talk about it. Now, the sales rep might ask, do you want this pump with the single volute casing or the dual volute casing? And the customer says, well, what's the difference? And the sales rep says, well, the dual volute casing is a $2,800 option over the single volute casing. So it's going to cost you more. And we don't stock that model. We custom cast that pump model against a firm order from a client. So the option is prepaid and delivery could take 2 or 3 additional months. And the customer says, well, no, is it efficient? And the sales rep says, well, sorry to say, the pump with the dual volute casing is not as efficient as the single volute casing. And the customer would say, well, the engineer didn't specify the casing, so let's forget about it. And therefore, we buy the pump with a single volute casing. Now, a few words about the design of the volute type pump. The volute type pump is popular in the chemical process industry because the discharge nozzle is located at the pump center line. The weight of the liquid and the discharge pipe and fittings are evenly distributed to the pump feed and the foundation. So you can see this picture right here. And you can see the weight of the liquid and the pipe above the pump in one of these pumps is distributed to the center line of the pump. And it's off to the side foot. One foot receives more stress and weight than the other foot. All right. So that's why you might want the center line design. Also, the impeller with the volute type pump is off-centered inside the volute housing. This cartoon drawing right here, it shows the yellow circle is mostly centered in the volute. And you can see that the impeller is mounted over to the side. So the impeller is not centered. The yellow circle is centered. The impeller itself is not centered. And this is for a reason, which we're going to discuss. The degree of eccentricity improves the pressure. So by off-centering the impeller, the pump will develop more pressure and it bumps up the efficiency of the pump. Most purchasers of this pump desire the improved head and the efficiency. And every time there's a good side, there's a downside. And the downside is the pump with this feature should be operated as close as possible to best efficiency. And the process engineer and the operator should avoid allowing that pump to migrate to the left or right of best efficiency on the performance curve. Now let's look at best efficiency on a process pump curve. And I'm noting process pump curve, not just pump curve.
Right.
So this wouldn't apply to your fish tank pump,
yeah,
or the radiator water pump on your car, or at a municipal swimming pool, okay? Now, this is a curve of a process pump, and there's the best efficiency zone on that pump, whether you're using, and I'll use my pointer here, that is the performance of the 6-inch impeller and the 8-inch impeller and the 10-inch impeller right here, okay? So this pump is available with all these different impellers, and this is the best efficiency of each of those different impellers. Now let's take the 10-inch impeller, for example, and that is the best efficiency zone. And this would be your operating zone. So if the operator of this pump should hold his flow meter to maybe 550 to about 625 gallons a minute and not let it drift from there. And as for pressure gauges, if this is water, this would be about 38 to 40 pounds of pressure from here to here, the pump company would call it 90 feet of head.
Right.
We could call it 38 to 40 psi of differential pressure across the pump. So if the operator is, he can see the differential pressure and he can see the flow meter, then that's where that pump should be operated as much as possible. And the pump should not be allowed to drift outside of that zone. And we're about to show why that is. Now, most engineers study hydraulics and pumps in a university course called fluid mechanics or fluid dynamics. And this is a text, typical university text that a mechanical engineer would study from. Buried inside this text are formulas and graphs of shaft radial force as a function of specific speed, which is one of the design indices of a pump. The specific speed as a design index, that's the reason that all boats, to consider a boat, all boats have certain parts that are similar, whether it is a fishing boat or a cruise liner, a tourist boat. All airplanes are going to have certain design characteristics, whether it is a one passenger ultralight or a 747 commercial jet. There are certain design aspects that are the same. And one of those is the specific speed. And the specific speed is a function of the design of the impeller. And there's this formula right here that's given in the book called the radial hydraulic force with these constants right here. And one of the constants that we're going to look at is the K value, which is the next couple of graphs. Now, that is also in a university text. This would be the Flexion formula for the single volute pump based on the specific speed. And this graph has elements of a pump curve. We've got the radial thrust factor. This is your side load. This is the stress on the shaft and the impeller and the rotating element. And this is radial thrust factor K versus the capacity of the flow of the pump. Now, when a pump is at 100% of design flow, that is the best efficiency point. Then less than 100%, the pump would be operating to the left of best efficiency, and greater than 100%, the pump is operating to the right of best efficiency. And these pumps should be held as close as possible to best efficiency. Now, this is the same graph, but with the dual volute casing. So that's your dual volute, and then back it up to the single volute. Notice here, specific speed of 4,000 with the single volute. And then here's your specific speed of 4,000 with the dual volute.
Right. So if I can interject my layman's interpretation of this,
sure.
The dual volute at the same speed has a significant reduction in radial thrust.
Yes.
And so going back to the single volute, the radial thrust is four times higher, I think.
That's right. That's right. Let's look at it. Okay, we've got basically 0.1 right here, and over here we got 0.4.
Right. And my
four times, yes.
Right. So my layman's example, which could be considered quite crude, and I really don't care if it is the ride at the amusement park where one is spinning around at a high rate of speed and then launches, and that's the radial thrust. It's the
yes,
projection from the impeller is creating radial thrust.
That's a good way to consider that. That's right. Yes.
All right, moving on.
Okay. All right. Now let's take this pump. That's a chemical process pump. It's got an 18-inch impeller. That's that right there, 18 right there. Okay. And the impeller is 2.5 inches from front to back. And the specific speed is 907. The K value at shutoff head would be 0.18, and the K value at best efficiency of 0.0079. We've got a shutoff head of 1,300 feet, best efficiency head of 1,220 feet, and a flow of 2,500 gallons per minute. Now, at best efficiency and applying the formula that we saw 2 frames before, let's go back to that formula right there, this formula, okay? So if we sub in and we're going to locate the force in pounds. And we were given the K value. I just showed you the K value. Then we've got the diameter of the impeller was 18 inches, and the vane and the shroud width, that's your B dimension, was 2.5 inches. And we've calculated the head at best efficiency and the head at shutoff head, meaning zero flow. Now, we come to this right here, and here is the applying the formula.
Sure. Sorry, if I could, if you back up one more frame, is that a dual volute? The last, the picture of that motor and pump, is that a dual volute right there?
That happens to be a single volute.
Single volute. Okay, okay. Please continue. I just wanted to, I was looking at that and I thought, you know, I wanted to find that out, but that's a classic example of a pump and motor right there. Okay.
Those are the design characteristics of that pump and its performance characteristics. So it doesn't matter whether it's single or dual volute, but it's going to matter how that pump is operated. Yes, it's going to matter that. All right. So when we work the formula at best efficiency, there's the numbers substituted at best efficiency. And the force is 172 pounds. And then when the pump is operated at shutoff head, the force is calculated at 4,558 pounds. And that is far beyond what the bearing can take. That is overloading the bearing, and it's going to fail, and the balls are going to break in the bearing, and the mechanical seal, the springs are going to break in the mechanical seal, and parts inside of the pump are going to burn and grind against each other rather than the pump running smoothly as it should, as most pumps will. All right.
Well, now, that 4,000 pounds represents the weight of a Humvee at the end of a shaft.
It's like hanging a big car off the end of a 2.5 foot shaft. Yes, that's as they say, that's going to leave a mark.
That's a hell of a
going to do some damage. And this is, you know, people say, well, why can't we get a handle on our mechanical seals? Why do we keep having bearing problems? And if you change from, you know, your standard lubricant to your high temperature, this is going to overload the high temperature bearing lubricant. This is going to destroy the lubricant in the bearing. That's way beyond what a pump and the bearing and the lubricant can handle.
That is a tremendous
amount. We've seriously overloaded that pump.
Yeah.
And that's just mathematical. It's just a mathematical.
Interesting.
Okay. Now let's take the radial loading and the and I'm calling it a percent of radial loading from 0 to maximum. And then we're going to take 100% of design flow would be your best efficiency flow. And then that is the graph of radial loading on the shaft. And right here, we see that the pump should be operated at about 90 to 110% of design. That's where the pump will give you its best service. That's where vibrations will calm down. This is where the mechanical seal will run 6, 8, 10, 12 years. This is where you'll get many years of service from your bearings. Okay. As the pump, as a process pump operates away from best efficiency, then the radial loading is going to go up and it reaches its maximum if the pump is deadheaded. And deadhead, it would basically be operating the pump against a shut valve or operating the pump against a totally clogged downstream filter, which is like a shut valve, or operating the pump against an overpressurized downstream header, which is like a shut valve. Then the pump should be operated at best efficiency. And now some people, when they write articles, and many of the pump companies will write an article or publish information. Well, the acceptable operating zone of this pump would be 80 to 120% of design. That's okay if it's a fish tank pump. Okay, that's okay if it's a recirculation duty pump. If it's a fire water pump, that's okay. But if it is a process pump, as we have defined it here, that's not okay. Unless you like to change bearings and seals, unless you like high maintenance. Okay. So these pumps are going to be problematic.
but to add to that, and again, we're talking about the process industry. Oftentimes, you're dealing with chemicals that are hazardous. So
Yes,
you're increasing your level of exposure to injury and all kinds of things. If in other words, if you're having to crack that thing open and replace bearings all the time because you're not running at your best efficiency point, you're also increasing your likelihood that someone's going to come in contact with a terrible chemical or breathe it or whatever. So you know the idea is wake up, get it in the best efficiency, keep it there, and have some longevity with your pump and your equipment, and you're mitigating all kinds of other challenges that would go hand in glove with operating it outside of that BEP or the efficiency
that's right.
point.
That's right. That's
Okay,
right.
that
All
makes sense.
right, let's continue. If you operate the pump away from best efficiency, these would be some of the problems that you'll be facing. Now, let's look at this here. Operating the pump to the left of best efficiency, we're going to have seal failures and elevated high vibrations that will not go away. Even after you balance the shaft, even after you balance the impeller, even after you align the pump, there's going to be some vibrations that will not go away. Um, we'll have premature bearing failure. And internal recirculation is a type of cavitation that occurs in a pump. So many people would call it cavitation, but
So
it's
as
a
a
type
result
of
of
cavitation that
cavitation,
occurs to the left
sorry.
of best efficiency.
So as a result of cavitation, you also could have a increased likelihood of impeller damage and failure too.
The impeller scraping and binding inside of the volute because they're very tight tolerances inside of this. It's a 3 to 6 thousandths of an inch. And so the impeller will be scraping and binding. And of course, you know what that's going to look like on a vibration meter. Yeah, the vibration meter just goes wild. Uh, and of course, and the bearings are going to be under a severe load, and the mechanical seal is going to be stressed. So this is maintenance. When the pump operates away from best efficiency, we're going to have maintenance on these pumps. Now, to be truthful, Vince, I get called to places where as soon as I walk into the plant, I realize the pumps don't have instrumentation. And I go into control rooms and the operators don't know what the differential pressure is across the pump because they don't have gauges because that information is not available to the operators.
And this is a
That
good,
most operators only know that the pump is either on or off with a green or a red light.
Larry. This is a good point. This is one that I think, and we may want to do another show on this, and that the value of gauges, but more importantly, the value of a good gauge salesman.
You
I
know,
don't think, I could be wrong, and I may get called out on this, but gauges shouldn't just be a pretty picture in an advertisement that has pretty gauges. I mean, I think that there should be some real effort to make sure that gauges are placed where they need to be, and we can get into that later. But I do see the value of not only a good gauge but a good gauge salesman.
a good gauge salesman. That's right. You're so right. Well, maybe we can plan on it.
Yeah,
We'll plan on another one about pressure gauges. So,
I'd
and
love.
I will take it from the not from selling the gauge and not from presenting the gauge and not from designing the gauge. We'll take it from if you have to use gauges, what do you need? If you have to use pressure gauges, this is what
Yeah.
you're going to want.
And I'll tell you what, honestly, I don't know what it is, but when I see gauges in advertising and so forth, I'm fascinated with them. They're kind of eye candy. They look interesting to me, and I do want to learn more about that. So let's kind of put a circle around that one. I want to do that, and I got some gauge people, and I want to bring to this too. So maybe we'll do like two or three or
Let's get some
four
gauge
guests.
people. Let's have the meeting with you and
Well,
me and a couple of gauge people,
I like it.
maybe
I
even
like it a lot.
competing gauge companies,
There you go. There you go. Let them.
competing gauge. Let them battle it out.
Sure.
All
Okay.
right,
Please
all right.
continue. That's
Uh,
a. I'm going to make a note of that.
Now, you and I were talking earlier, and you asked a question. Let me see if I can back this up to here. No, let's see. back this up to here. No, won't do it. Okay. You were talking about a filter. Let's, hang on a second. We'll come back to here. Right here. Okay. No. Okay. Nope. I guess, okay, we'll have to do here. Now, all right, when a pump, okay, can you see my cursor?
Yep.
When a filter is new and clean, the pump tends to run out here on the curve. As the filter gets dirty, it drags the pump back to here on the curve. And when you reach a certain pressure across that filter, the filter media should be changed. The filter screens should be changed or cleaned. Then what typically happens is we're in the middle of a process and they can't stop it. So the process engineer says, we can't stop the pump to change the filter. We'll change the filter next weekend. Well, by the time the weekend comes around, your pump's running back there. But nobody knows it if you don't have gauges. So we're running now at zero flow or at this flow right here, because as the filter gets dirty, it drags the pump back to here. Then you stop the pump, you put in a clean filter, and the pump migrates back out to here and starts working its way as the filter gets dirty again. Okay.
Gotcha. I got you.
All right. You open a valve, you open a control valve, the pump is out here. You pinch the control valve, the pump is back here. You close the control valve, the pump is here. All right. And the reason that a car has a steering wheel is because the roadway moves. And the purpose of the steering wheel is to hold the car in the lane. So here's what you would do. Say you put in a new filter and the pump migrates out to here on the curve. Then the operator would pinch a control valve and drag the pump back to here with the control valve. Then as the filter clogs and gets dirty, the filter will pass the control valve and then brings the pump back to here. Now the operator will open the control valve and relax the resistance. All right. So and of course, this is like keeping your car in the lane of traffic. That's why the car has a steering wheel. So the operator must control the pump. That's why we have operators. That's why a car has a steering wheel. Now let's go back up to where we were here. We had gone through this information here, and these would be some of the problems that you will face if the pump is allowed to operate away from best efficiency. And of course, these are most of people's complaints. Some vibration programs are going on to 20 years, and they are still going on, and they have yet to solve the problem. And like I say, if you've got a vibrating tire on your car because the tire is unbalanced, you take your car to the tire shop and they hammer those little weights onto the wheel rim, and the vibrations go away or they calm down.
Yeah.
Then you say, well, we've got a bent shaft. Then if you straighten your shaft, then the vibration should calm down. So we have an unbalanced impeller. Well, then if you balance the impeller, then the vibration should calm down. So, well, we have some misalignment between the pump shaft and the motor shaft. Well, if you align the pump shaft to the motor shaft, the vibration should calm down. Then why does the vibration program go on for 20 years?
Good point. I was just doing some quick.
And I'll give you the example. If you're driving a car in fourth gear at 5 miles per hour, your car is going to vibrate. And it's not because there's an imbalance or a bent shaft or misalignment. It's because you're not supposed to operate your car at 5 miles per hour in fourth gear. Your car is going to jerk and vibrate. And the same thing is if you're driving your car at 60 miles per hour in first gear, your car is going to vibrate. And it doesn't mean that there's an alignment problem. It means you got an operational problem. And when the pump operator does not know where the pump is on the curve, that is an operation or a design failure. It is not a maintenance failure. But we like to blame maintenance. Those mechanics don't know how to install a mechanical seal. Those mechanics don't know how to install a good set of bearings. We're using the wrong lubricant on the bearings. And this is why we keep having, this is why we do all kinds of things to improve the reliability, and reliability does not improve significantly.
Well, this is why I'm doing this, Larry. This is exactly why I want this out there, is that there is no, uh, I don't think there isn't any resource out there where somebody could look at a problem and see some of these options that you're bringing to the table. So it's this is the whole purpose of doing this, is to
Yes.
bring this kind of information out there. We are not endorsing any one product, any one pump, or anything. It's just saying, this is what you've encountered over the years that may be helpful to somebody that's coming up in the industry, or maybe somebody that's just never been able to figure it out before. So please continue. This is
All right.
great
Well,
information.
the design of the dual volute casing resolves some of the stress by centering the impeller within the secondary volute wall. So we see this right here, and I showed this frame earlier, but I'm going to haze out part of the picture right here. You'll notice that at the dual volute pump has become opaque, except for certain parts of the pump, the internal parts of the pump. And what we can see now, comparing to the single volute, within the dual volute, let me use my cursor right here, this distance from here to here is the same as this distance from here to here. And this distance from here to here is the same as this distance from here to here. So within the second volute wall, the impeller is mostly centered, and therefore all radial forces are in equilibrium. The balance between the pressure and the velocity and the area exposed to pressure and velocity are all equal in the dual volute casing. All right. Now, we showed you that graph earlier, and if we go to the dual volute casing, that would be the graph of radial loading of the dual volute casing. Certainly, it's good to operate the pump at best efficiency, but even if the pump is being deadheaded, why is the pump deadheaded? Because the filter clogged 3 days ago and we couldn't stop the pump to change the filter, because somebody in a maintenance function, somebody installed a check valve backwards into the pipe, and we just now discovered that the check valve was installed backwards into the pipe, and the pump's been deadheaded for four days. It frequently happens that a production engineer will order to increase the flow because he's got a big order from a good client. And so they say, run the pump. This pump is designed to run at 600 gallons a minute. Let's run the pump at 800 gallons a minute. And the production engineer does not know what he's doing to the pump. He's only trying to meet a production schedule, right, so that he can sell more product.
Right, but clearly in that last example,
yes,
the dual volute has, in again, my layman's interpretation, much more of a forgiving aspect to it as far as radial load goes.
Yes.
So you can run it at 160% or 60%, and the effect is significantly lower, by a factor of 5 in some cases.
Well, remember when we saw the graph, it was a 4-to-1 relationship.
Right. So for the $2,800 and the 2 extra months that it takes to purchase the dual volute casing, I could see where the advantage would come in. And a good salesman should share that and say, look, no, it is going to take 2 months, and it's a special order, and you got to pay in advance. However, I mean, this part needs to be explained too. Why?
Yes.
Why would you want that? Well, here's why you want it, because you have much more forgiveness.
That's right.
Yeah.
That's right.
Yeah.
Well, let's go back to the beginning of this lunch and learn with Vinny. And when the pump sales rep says, do you want this pump with the single or the dual volute casing? And the client said, oh, I don't know. What's the difference? Well, an astute pump sales rep could have responded, if you know that this pump will operate at or close to best efficiency, the single volute pump casing is your best option. All right. And then if he has to explain that further, he said, oh, I'm talking about your fire water pumps. I'm talking about your recirc pumps. I'm talking about your service water pumps. I'm talking about the cooling tower recirculation pump. Okay, that you don't really need it, but and then the sales rep continues, if the demands of the process require that the pump must operate for more than a few minutes away from best efficiency, or if the pump must operate while deadheaded against a closed valve or against a clogged downstream filter, or if the demands of the system drag the pump all over the performance curve, then the dual volute casing is your best option. And I think we said, you know, how do we end it here? The customer is armed with the information that he needs to purchase the best pump for his company. And the customer may have other questions. How much does it cost? And the salesman can say, well, it's a $3,000 option, which is about the cost of one mechanical seal. So how many mechanical seals have you wasted over the past 15 years? It's a cost of a couple of sets of bearings. And then the customer says, well, is it as efficient? And the answer is simply, it's not as efficient, because designing that second wall into the volute casing is an obstruction, and it does interfere with the flow. Therefore, I cannot say that it is as efficient as the single volute pump, but it is the best pump for this app. It is by far the best efficient pump for this application. Your pumps that must operate all over the curve, because you've got filters and heat exchangers and inline mixers and flow meters and cyclone separators and pressurized tanks and levels that go up and down in the tanks and temperatures that go up and down. Everything is going on in the chemical process, and your pumps are just being dragged all over the curve. Then the dual volute casing is a pretty good option.
Yeah,
It's
Larry,
about the cost of a mechanical seal.
That's pretty good information. And I'm wondering if we could just pause for a minute. Maybe you can take away the PowerPoint and just chat with me for 1 second. I want to.
Well, let's stop sharing. We'll go.
I want to. Yeah, I want to bring up the and provide a small commercial break.
Little commercial. Okay.
Yeah. Well, I mean, I want to brag about your product, the Orit, the little Orit device that you've got.
The O-ring Identifier tool. That's this product right here. You can see it's about the size of a pen or a pencil right here. About the size of a pen or a pencil.
And you invented this how many years ago?
About 40 years ago.
Wow.
40 years ago. I'm not actually the inventor. My daughter is the inventor. She's approaching 40 years of age. When she was little, she was very athletic, and she would run through the house with the ball, bouncing the ball and throwing the ball against the walls. And one day she was throwing a super ball. She had a super ball, and that gave me the idea. I was working in a refinery, and we had some serious problems with O-ring errors. Specifically, it was depropanizer reflux, if I remember, was the liquid. And we were having numerous mechanical seal failures, which on analyzing the failure proved to be O-ring failures. So the O-rings were degenerating on the mechanical seals, causing the seals to leak and causing the pump to be shut down. So we were saying, well, there must be a way of analyzing an O-ring, determining the composition of the O-ring so that we are positive that we're using the right O-ring. And just then my 2-year-old daughter ran through the house with a super ball. And I noticed, look how high the super ball bounces compared to a regular rubber ball. And that gave me the idea, and started playing around with different designs, and had some copper tubing and a little weight, ball weight, and continued to refine it to this point right here. Maybe you can see.
Sure.
It's got some calibrations on it here. Right. well, maybe not.
Yeah, I can see it.
Right. Those are different calibrations, and they will say what you're holding in your hand is a Viton ring or a Calres O ring or a nitrile O ring or an ethylene propylene O ring. And you can, this is a little non-destructive test, and it's got a pocket clip, so it'll fit right into your shirt
Right.
pocket right there, just like a pen or a pencil.
So
And
how could somebody get one of those today if they wanted one?
you can contact my company, Bachus company. Look it up on the internet, and we have plenty in stock, and we ship this all over the world to hydraulic users, and I would say just about every valve manufacturer uses this. Every pump manufacturer uses this. Hydraulic cylinder manufacturers, process gauge companies purchase this, and other companies, chemical plants purchase this and pass it out to all the mechanics. They'll put 200 units into the storeroom and pass it out to every mechanic. It's part of his company toolbox.
Sure.
Companies like Boeing and the U.S. military, NASA are clients, and they all purchase this. And it has no batteries and no digital display. All you need is one eye.
Yeah.
Just one eye,
And
you can determine if the O-ring that you're holding in your hand is of a certain composition. So
that's amazing.
that's the
Right.
O-ring identifier.
Okay. Well, and they can get that at the Bacchus Company website.
Yes. In years gone by, we have had distributors, and in some cases, we have a distributor in Australia and a distributor in Europe. And we handle most of the Western Hemisphere, North and South, out of my office. So, and you commented one time, why do I have the file cabinets? Because I'm running a company. You say, well, it looks like you're unorganized if you have file cabinets. No, most people don't have their own company. I've got my own company, and that's information in file cabinets. And I'm constantly going around and around with the IRS. So sometimes you got to have paper copies.
Absolutely.
So anyway, that's why I have the file cabinets behind me.
I don't blame you at all. I've got mine right here. All right, so let's jump back in. We got a little bit of time left, and I don't think you're completely through with the dual volute.
I think that I was. Yes,
okay.
I think that I was. Unless maybe let's go back to screen share and
sure.
Come to here. Let's see. Let's do it here. And yes, okay. So so we were here, and then that's me with a pump. That's a pump. Okay, they can be big. You're not going to pick that thing up.
No.
And the material for this workshop comes from this book. So that's another book that I have written right here. Everything that you need to know about pumps, everything that I just said today is in that book.
In English and in Spanish.
And it's available in English and in Spanish. That's right.
Awesome.
And anybody that wants to contact me, the web address is bachusinc.com. That's Bachus Incorporated. That's where that comes from. And my email is Larry@Bachus Inc. And the phone is 615-361-7295. And that was everything that I had planned on showing you today.
Oh, wonderful. Well, let's plan another one of these. These are great, Larry. I can't thank you enough for taking the time to share this information. And folks, again, if I can get you to please like and subscribe, give me a thumbs up if you like what you're seeing here, and copy and send it to your friends if it's something that you find that it would be beneficial. I know YouTube is a very large format where, I realize that there are a lot of choices you can make, but this is very specific to the pump and motor and valve industry and rotating equipment. And Larry, you're just a font of knowledge, and I can't thank you enough for taking the time.
Glad to do it, Vince. It's always good to get together with you.
It's a pleasure.
And I like your questions because you speak where other people are afraid to ask a question. And that's, it's like, you're like a child, a little child doesn't mind saying, why is that? Why does that happen?
Tell me why
does that happen?
There you
go. So an adult would say, oh, if I ask that question, he'll know that I don't know.
Yeah.
And that's the wrong attitude. So I like it because it's like talking with you, it's like talking with my children.
We're gonna.
They ask that
Yeah.
for a reason.
Well,
Why,
I want to
Daddy?
know
Why
why.
is that?
I want to
So
know why.
why?
Yeah.
Why?
So there
It's
you go.
always fun to talk with you, Vince.
Thank you, Larry. It was a pleasure, and we'll hopefully see you next time, folks. Thanks for
Next time,
joining.
we got to work on pressure gauges.
That'll be a good one. We
I
should.
think that'll be a good one. I think that'll be a good one.
All right.
All right.
Thank you, folks. Thanks again for joining me on Vince's Lunch and Learn.